In our previous probability lectures, we talked about what would happen when one event occurred. Let's take a look at what happens when two or more events occur. This brings in probability theorems 6 and 7. So we'll look at what those are and how they can be applied given probability statistics. Theorem 6 talks about independent events. What independent events are two events that the occurrence of one does not affect the probability of the occurrence of the second one. So you can think of, we have 3 apples in a box. We have one red one, one yellow one, and one green one. So the probability of picking a red apple is the same as picking a yellow apple, and that's the same as picking a green apple, 1 out of 3, because we have one of each. Independent events is considered generally sampling with replacement. So if we reach in our box and we pick out the red apple, that was a probability of 1 out of 3. Now we put the red apple back. We pick again. This time we pick the yellow apple. The probability of that occurring was 1 out of 3 again because we put the red apple back. If we didn't put the red apple back and then we picked a second apple, the probability of picking a yellow apple would change to 1 out of 2. But since we put the red apple back, the probability of picking the yellow apple in our second trial is not changed from what it originally was. And that is independence. Independence is not the same thing as mutual exclusivity. So if we have our two events here, A and B, they're not mutually exclusive, but depending on how we pick, they may be independent. So keep that in mind when you're calculating your probabilities. Theorem 6 states that we have two independent events, A and B. The probability of both A and B occurring is the product of their respective probabilities, whether or not they're mutually exclusive. So the probability of A and B is probability of A times the probability of B. When you see this "and" here, that means that we have more than one trial. So "and" means more than one, or refers to mutual exclusivity. So "and" is independence. Let's take a look at this example. So we're going back to our box of 300 parts. We have the same X, Y, and Z numbers of conforming and non-conforming parts, and we want to figure out the probability that two randomly selected parts will be one from X and one from Y. We're going to assume that the first part is returned to the box before we pick the second part. When you see return to the box or return to whatever container is holding these parts, that means we have independent events. The two selections means that theorem 6 or 7 is going to apply because we have more than one event occurring. How do we calculate this? Let's take a look. So we want the probability of X and Y, so that means we're going to multiply. Probability of X, picking a part from supplier X, we've got 72 parts from X out of 300 parts. That's our first trial. Our second trial, okay, we want the probability of picking a part from Y. We know that there's 142 parts from Y, and since we put the first part we selected back, there are still 300 parts in our box, and so that's why we're dividing by 300 instead of a different number. So when we multiply through, we get a probability of 11.4%. And that's reasonable for this. When you start multiplying probabilities together, you're talking about events occurring in series. So the probability that both of those events are going to occur is probably lower than you would expect given another scenario. So if this was X or Y, we would need to add these, and we'd have a much higher probability because we'd start adding 72 to 142, then dividing by 300. But when you have two events occurring in series, that the probability of one then the other occurring, that's a event in and of itself. So it's going to have a lower probability. Theorem 7 states that if A and B are dependent events, so the occurrence of B depends on the occurrence of A, the probability of both A and B occurring is the product of the probability of A and the probability that if A occurs, then B also occurs. Mathematically, this looks like this. We have the probability of A and the probability of B given A occurred. So this is sampling without replacement. We pick one part from our box, then we put it to the side, we don't put it back in the box, we pick a second part. Again, this has nothing to do with the event overlap. We could have A and B overlapping right here, but this is talking about separate trials instead of things going on in the same trial. So you can have dependent events that are not mutually exclusive or dependent events that are mutually exclusive. Let's look at an example of Theorem 7. So we're back to our box of 300 parts. We want to figure out the probability that two randomly selected parts will be from one supplier X and two supplier Y, but we're going to assume that we pick one part and we do not put it back in the box before we pick the second part. All right, so this starts out the same as the example of Theorem 6. We pick a part, the probability of selecting a part from supplier X is 72 out of 300 parts. We've got 72 from X, we've got 300 in our box total. That's where these numbers come from. Now, we take that part out, whatever it was, and we put it to the side. That means instead of 300 parts in our box, we have 299 because we took one out. So when we're looking at the probability of selecting a part from Y, we still have 142 because we're assuming that the first part that we pulled out was a part from X. So we're assuming that this occurs. Then we have to divide by the total number of parts in our box, that is our overall probability space. That is not 300 this time, it's 299 because we did take that one part out. So this time we have a probability of 11.4%. That's slightly higher, just slightly, than our probability when we put the first part back in the box. And that's because if we chose a part from supplier X the first time, then there are more of parts from supplier Y compared to the total number of parts if we didn't put that first part back than if we did put it back. Changes it just a little bit, but it's enough to give us a different answer. To recap which theorem you use in which situation, if you have one event occurring, you're picking one part or one can or one product out of a set of many, you use Theorem 3 when you have mutually exclusive events. So there's no overlap between the events occurring in that one trial. You use Theorem 4 when you have non-mutually exclusive events. So there is some overlap in their probabilities in that one trial. If you've got two or more events occurring, then you use Theorem 6 if your events are independent. So the probability of one event happening does not affected by the probability of another event occurring before that event. If your events are non-independent, so the probability of your second event is dependent on what happens in the first trial, then you're going to use Theorem 7. Theorems 1, 2, and 5 are more general probability theorems, and they apply regardless of how many events you have going on. But when you're deciding between one event and two or more events, that's when what theorem you use makes a difference. Also remember that you can have independent events that are mutually exclusive or non-mutually exclusive. You can have non-independent events that are mutually exclusive or non-mutually exclusive. Independence and mutual exclusivity are two different things. So make sure you keep those straight and that you realize that you can have both, either, or neither occurring at the same time.